Hello, Bobcats. This is 2330, Chapter 11, Part 3. I'm going to give you an overview of NMR spectroscopy, both proton NMR or hydrogen NMR and carbon NMR. Okay. So when we talk about NMR, that is a name for nuclear magnetic resonance spectroscopy. So as the name suggests, we're going to use a high magnetic field to affect the nucleus of the atom, specifically the protons and neutrons inside the nucleus of the atom. And then we're going to look at how those change to give us information about the molecule. For example, how many types of hydrogens we have, or how many different types of carbons we have, and then what kind of things are attached nearby. Okay, so the basic idea here is that just like electrons have 1/2 spin, and if we think about our quantum numbers, they can be +1/2 or -1/2, and they like to pair up when we have them here. Well, the protons and neutrons inside the atom also have this same kind of spin associated with them. Now, spin can be aligned in a magnetic field. So if we had a high magnetic field, we can get those spins to align with the magnetic field, and they can be up or down depending on how they first get aligned. And then what we can do is we can take that alignment in that field and start looking for things that are similar to each other or different from each other by how they interact in that field, okay? So, for example, in proton and carbon NMR, once we apply the magnetic field, it can only be aligned with the magnetic field. In the top one, we'll have it with magnetic field, but the spin is down, so that counts as -1/2 spin. And if they're aligned with the field, we have +1/2 spin. Okay, so they have to be aligned with the field. Notice on this side of the slide here, before we apply the magnetic field, they can be in any orientation they want. There's no reason for them to be in an orientation until we apply that magnetic field. Once we apply that magnetic field, they have to line up either with it or up opposite it, and then we can actually do some interesting probing on that to see which way they can go. Okay, so let's continue. Oops. Okay, so there's some very important things about NMR spectroscopy, and the first thing is resonance, okay? The absorption of the electromagnetic radiation by the spinning nucleus is a result of flipping the spin from a lower energy state to a high energy state. Okay, so just by putting the nuclei into a magnetic field, we get them to align, okay? Now, if we can hit that with some form of radio frequency radiation, what that'll do is that'll take some of the ones in the lower energy and flip that spin, okay? Now, once it flips that spin, if it's in a higher energy state, because we've done this, what it's going to do is it's going to relax. And the time it takes to relax back down to that lower energy state, that's what we're looking for when we're looking for that signal that we get out of the NMR. Okay. So what does an NMR look like? Well, they tend to be very big machines because in general, we use superconducting magnets, and superconducting magnets have to be held at 4 Kelvin right there, which means that we have a huge thing filled with liquid helium to keep them that cold. We apply a magnetic field when we're setting that up, and then it maintains that magnetic field as long as it's that cold. So this is a very powerful magnet. And then inside that magnet, there's a place that we hold the sample. And this right here is our sample tube. Is where we put our chemical that we're putting our sample in, and it's held inside 2 coils. One coil is going to pulse it with the radio frequency. The other one's going to sit there and listen for it to relax. It'll listen for the output radio frequency when it does that relaxation. So we pulse it and then wait and listen for the relaxation. Okay, so when we do this, we are we can do this multiple times where we pulse it, listen, pulse it, listen, pulse it, listen. And by averaging out all those signals, we get a very strong signal that lets us identify and have a very good spectrum of very good data. Okay, so now that we have this idea that we've taken our nucleus and we can put it in a magnetic field, align it, and then flip them and then wait for them to relax back, the time it takes for them to relax is based on what we call chemical shift, okay? So the electronics around that nuclei change how that chemical shift is. And so our chemical shift is typically measured in parts per million, which is really, if we think about it here, on the spectrum down here, we start at 0 parts per million here, and we move up the scale here. So if we're thinking about this as time, it's going to take, this starts out as our 0 time, and then this is the time it takes longer and longer to get these out. And so that that's why we look at this in frequency in hertz, is per seconds it takes to do it. And so technically we're looking at a time regime in this direction, but every different chemical interaction has a different time it takes to relax. And that different time it takes to relax is what we call chemical shift. So certain, like hydrocarbons, will always take this long to do it. Ethers will always take this long to do it. Hydrogens that are on an aromatic ring will take even longer to do it. And so by looking at that regime, that ppm shift, we can actually tell the different types of hydrogens we have or the different types of carbons we have. Okay, so if we look at this huge table here, and what I want you to see is there's some general trends here, is that when we have like sp3 hybridized carbons, they are in this regime here. It doesn't take them very long to relax, and therefore we have very small shifts. We start our shift at 0 and we go out to maybe around 2 if they're close to a double bond. Once we start getting in the regime with double bonds, where we have aromatic rings and double bonds, these get shifted up above that, right here into the 2 to 3 range. Okay, so what also affects that relaxation is having hydrogens bonded to electronegative atoms. Okay, so if we look at here, if we have that hydrogen bonded to something near an oxygen or a nitrogen, they tend to be shifted higher. So it takes longer for them to relax. And so we can actually see that those things are bonded next to an oxygen or a nitrogen. Once we have them shifted where we have them next to an sp2 hybridized carbon, like a carbonyl here, we also get a shift above that of the regular hydrocarbons, and we start seeing them shift higher and higher into the 2 to 4 range. Okay. Now, if we have a halogen next to it, halogens tend to be big and have a lot of electronegativity, and so that shifts it even higher than we would see with an oxygen or a nitrogen. Once we get to the aromatic systems and double bonds, they get shifted even higher still, up into the 4 to 5 range. Aromatic rings can be in the 6 to 8 range. And then once we get to these aldehydes and these carboxylic acids, they get shifted much, much higher into the 10 to 13 ppm range. Okay, so the thing I want you to remember is that as we change that hybridization of the carbon, the hydrogen attached to it starts taking longer and longer for it to relax. Therefore, it has a higher and higher chemical shift. Okay. So when we're thinking about signals, we are thinking about where they are and what kind of splitting they have. So a particular type of hydrogen that will peak at a certain shift based on where that chemical shift is. And so we get a peak just for that hydrogen, okay? But because there are hydrogens on adjacent carbons, or adjacent atoms, those hydrogens there are not the same as this one, and therefore they interfere with the signal, and we get what we call signal splitting. So the hydrogens that are adjacent to that hydrogen we're looking at will split that signal. And so in general, we have what we call the N+1 rule, which means we get one peak for the hydrogen that we're looking at that specific shift. And then we add to it all the hydrogens that are one carbon over, okay? So let me show you what that looks like, okay? So in the case of this 1,2 trichloroethane, let's look at the signal real quick here, okay? So we have two types of hydrogens here. We have a hydrogen that is what we call the A hydrogen, or just it's there. And we have two hydrogens on that carbon right here. Let me draw it. Okay, so we have two hydrogens on that carbon, and we have one hydrogen on this carbon. Okay, so the first thing we look at is the shift. The part that they've shifted over is based on what is attached to the carbon we're looking at. Okay, so if we look at this carbon here, okay, we have two chlorines attached to that. Okay, because there are two chlorines, not chlorine 2, just two chlorines, because we have two chlorines attached to that, it's going to be shifted up higher than the carbon here with just one chlorine on it. So this has one chlorine on it, okay? So that's going to tell us that this is going to be the lower peak, and this is going to be the higher peak because of what's attached to that carbon. Okay, so that's our shift. That's the first thing we look for. Now we have to look for the splitting, okay? So this hydrogen here, we get a peak for the hydrogen, and then we get a peak for each hydrogen on an adjacent carbon. So we have one for this hydrogen, and then we have 1, 2 next to it. So that means we're going to have a total of 3 peaks. Remember, it's N+1. So our peak here is 1 peak, and then N is all the hydrogens next to it, and therefore we end up with 3 peaks on that carbon, okay? So now let's look at the next one here. Let's look at this carbon here. These hydrogens here. Okay, those hydrogens are shifted because of what they're attached to, so we get 1 peak for that, and we have 1 hydrogen attached next to it. Okay, so we have 1 peak for the hydrogen itself, and then we only have 1 hydrogen in adjacent carbons. Therefore, we're going to end up with a total of 2 peaks here. So this is going to be a doublet, or 2 peaks, and this is going to be a triplet, or 3 peaks. Okay, so let's try that again on a different molecule, just so we kind of solidify that N+1 concept to us. Okay, so let's take this other compound here, and if we look at this compound here, we have a total of 3 types of hydrogens. We have the hydrogens that are just bonded to the end of the group here. We have the hydrogens that are bonded here in the middle. Those are not like the hydrogens here because these are bonded to carbons, and then this is bonded to a carbon with a chlorine, so they're different. And then we have our last type of hydrogens here because this is bonded to a chlorine and also bonded to a carbon. Okay, this one, the middle one here, is only bonded to carbons on either side, and this one is only bonded to a single carbon, and then there's only hydrogens there. So that's why there are 3 different peaks, because we have 3 different shifts because they have different things bonded to those carbons. All right, so now we have 3 different peaks, okay? Now, just empirically, we think that this is the most electronegative atom, so this is going to be the highest up in our system. This is going to be our next highest up because it's one adjacent to it. And then this should be our furthest down that way, okay? So this is going to be our middle peak. This is going to be our lowest peak. This red one here is going to be our lowest peak. And this blue one's going to be our highest peak. All right, now, the other thing we need to think about is how many splits we're going to get for this, okay? So let's talk about this one first, right here. So we get our N+1, okay? So we have 1 peak for the the hydrogens that just exist, that's our 1. And then we have N, the number of hydrogens on an adjacent atom. So in this case, we have 1, 2 hydrogens plus the 1. So our furthest down peak, our blue peak here, should have 3 peaks. 1 for the hydrogens on the carbon, and then 1 for each of the hydrogens next to it. Okay. Now let's take a look at the last one right here. Let's look at this one right here. Since it's going to be up our highest, we get 1 peak for all of the hydrogens here plus our N. And we have a total of 1, 2 hydrogens next to it. So this peak is also going to give us a splitting of 3, or 3, a triplet right here. Now let's look at our 1 here in the middle. Okay. So our 1 here in the middle, we're going to get 1 peak for just these hydrogens here, but then we have 1, 2, 3, 4, 5 hydrogens next to it. So that's 4 plus 5, which means we're going to have a total of 6 peaks on this one. Okay, just because those are the number of hydrogens on adjacent carbons that we have. All right, so that being said, we're going to have, these are going to be in the middle and have 6 peaks. These are going to be furthest down and have 3 peaks. And these are going to be up highest and have a total of 3 peaks. So now let's look at the spectrum, okay? Okay, so when we pull it over here and look at our spectrum here, we have our highest number of peaks right here, which is the 2 hydrogens that are the ones next to the chlorine atom right here. And we have a total of 3 peaks, which is what we predicted. Okay, and the ones furthest down right here, these hydrogens here, we know that they were going to be split into a 3 peaks. So we have a 3 peaks here. And what we also find out is in the middle here, we have the ones we predicted to be in the middle, and it has 1, 2, 3, 4, 5, 6 peaks in it. Okay, so we predicted those 6 peaks because there were N plus those 5 other hydrogens. And so we've actually identified its shift by what it's attached to it and the number of peaks it splits into. Okay, so that's what the general concept of shift and split is in proton NMR. Oops. When we move to carbon NMR, the way we do that is that the carbon has to be, the carbon-13, it has to have an odd number of protons and neutrons. And it does the exact same thing. It shifts, but in general, the carbon shift is a lot bigger. And when we do carbon, we actually do what we call decoupling, which means we take away the splitting caused by hydrogen. So that means we only get 1 peak per carbon, irrelevant of how many hydrogens are on it. But all we're looking for is the shift. The shift in the carbon tells us what kind of things are bonded to it. Okay, so if we look at a carbon NMR spectrum, and we look at this compound here, we have how many types of carbons here? We have a carboxylic acid carbon that's bonded to a carbon that's bonded to an oxygen. That's 1. We have a CH2 group that's bonded to a carbon and a carboxylic acid. Now this is also a CH2 bonded to a carbon and carboxylic acid. So those are the same. So that's a different type. So now we have our A is one type, our B is another type. We have our C carbon here. That is attached to an oxygen and a carbonyl right here. So we have a 3rd type, C, and these two are equivalent because they both have CHs next to a thing, and that's going to be D. So we have 4 different types of carbons, okay? So let's think about their shift here. These are most like regular old hydrocarbons, so we think they're going to be the lowest down on the list because they have the fewest number of electron-rich atoms on them. Let's see, we have the next one. This one has a lot of carbons attached to it, but it also has this. So this is going to be probably our second peak on the system because we have an electro-rich oxygen here, but then we have other carbons attached to it right here. This one right here is going to be probably our next one up because we have it bonded to a carbon that's bonded to other things. So it's probably going to be shifted higher than that. And I think this is going to be our third peak. So let's take a look at that right here. So the one most like our hydrocarbon here is the one down here, this B. It's going to be our lowest one. And what we see is we see a peak down here. It's almost like a regular hydrocarbon shift peak. Then the next up is, looking at C here, it's the one that's bonded to the oxygen. This is only bonded to carbons. Then these two right here are the ones that will have carbonyls on them, and they are shifted slightly differently because of what's bonded next to them. And we see those shifts as well. Okay, so the idea here is that different functional groups do different shifts, but we don't have to worry about splitting because the hydrogen has been decoupled from the system, and we have a single peak for each type of carbon we have. Okay, so let's talk about our chemical shifts. And our chemical shifts move along with what the hybridization on the carbon is. So our lowest chemical shifts between 0 and 50 ppm are sp3 hybridized carbons, okay? With our tertiary carbons being slightly shifted higher and our primary carbons slightly shifted lower, okay? The next thing we have is our sp3 hybridized carbons, but they're bonded to an electronegative atom like nitrogen, oxygen, or a halide. Okay, that's going to shift things just above 50 to the 80 range there. So things that have an ether or an alcohol in them are the carbons that are associated with that are going to be shifted slightly higher. Once we get to hybridization of sp2, that shifts us into the 100 to 160 range. And that includes aromatic compounds like benzene because we have an alkene, we have sp2 hybridized carbons there. Once we form an sp2 hybridized carbon, but then we also have an electronegative atom in it, just like here we've shifted from sp2 having an electronegative shifting up, we shift those higher from 160 to 180. So you can think it's sp2 hybridized, but it also has an electron-rich atom. And then if we have very little donating available to us, see, we also, in this case, we have a carboxylic acid, so we have oxygens nearby. If we don't have that oxygen formation, we get shifted a little bit higher to the 180 to 200 range. So we can actually look for different functional groups based on their hybridization of the carbon. Okay, so here's a table of the different shifts here. Most like an aliphatic hydrocarbon or sp hybridized here are going to be in the lower range here. Once we have electronegative atoms attached to them, we start shifting up in range into the 50 to 80 range. Now we are looking at our sp and sp2 hybridized carbons here. Then once we move to our carbonyl type compounds, we ended up shifting well above the 150 range into the 200 parts per million. So just looking at that shift as a function of hybridization is a good way to tell which functional groups show up where in your carbon NMR. And that is the overview of proton and carbon NMR we will be using in this class.